next we will see the interrupt process, like when an interrupt occurs, then how that interrupt is serviced in 8085, both the non-vectored interrupt and the vectored interrupt. So, we will first look into the non-vectored interrupt. The non-vectored interrupt process is like this. First of all, the process should be enabled using the enable interrupt instruction. So, if this enable interrupt is not executed by the processor, then the processor will not be able to receive any of the interrupts. In fact, when the processor is reset, this enable interrupt, this is all the interrupts are enabled, and for the purpose of different programs. So, it may so happen that the interrupts have been disabled through the DI instruction. So, if this EI is not done, then this interrupt will not reach the processor. So, the first thing to ensure is that the interrupts are enabled using the EI instruction. Now, as we know that interrupt can occur at any point of time during execution of instructions by the processor. So, what the processor does is, irrespective of the point at which the interrupt has occurred. So, interrupt will be checked, whether the processor will check for the interrupt at the end of every instruction. So, typically in the last machine cycle, the interrupt the interrupts are checked, whether any interrupt has occurred or not. So, we will see after a few lectures that how to decide, like for how much time this interrupt pin should be activated to get an interrupt. So, we can understand that the interrupt should be activated for at least a complete duration of one instruction. So, if we look into the instruction set, whatever be the largest instruction execution time, so the interrupt must be enabled for that much of time to get the interrupt detected. So, if the interrupt occurs, then what the system does, the microprocessor will first complete executing the current instruction. So, this is very important thing to note. It is not that interrupt has occurred and the processor will leave the execution in the middle of an instruction and go to the interrupt service routine. It does not happen like that. The first thing it does is the interrupt the current instruction that the processor is executing is completed, and once the instruction is completed, then it will start a restart sequence. How that interrupt service routine can be started? So, that is the restart sequence. So, first of all, this restart sequence will reset the interrupt flip flop. This is the first thing that is done. So, the interrupt enable flip flop that we have seen, so that will be deactivated at the beginning of this restart operation, and it activates the interrupt acknowledge signal. So, this non-vectored interrupt in 8085, INTR is the non-vectored interrupt line. So, when that interrupt is detected, the processor will first reset the interrupt acknowledge interrupt flip flop, and then it will activate the interrupt acknowledge signal INTA. As we know that INTA is an active low signal. So, this will be made low to make it active. Now, the protocol is like this, that interrupt acknowledge line should be connected somehow to the device which has generated the interrupt, and on getting this interrupt acknowledgement, the device should provide some address from which the interrupt service routine has been located in the memory. Now, as a system designer, we will know like in which at what memory location the interrupt service routine for a particular device has been loaded. So, the ISR address should be provided by the device, and how is it provided? It is provided by means of some RST instructions. So, there are 8 RST instructions, and any of these each of these RST instruction is of the format RSTN, where n is a 3-bit number, and then this RSTN is a single byte instruction. So, what happens is that upon getting this interrupt, the processor enters into an interrupt acknowledge machine cycle. In this interrupt acknowledge machine cycle, this interrupt acknowledge pin is made low, and it is expected that on the data bus the opcode for one of the RSTN instructions will be available, and upon getting that particular opcode, so processor will decide to which address it should go, and accordingly it will go to the corresponding address. So, when the processor executes this RST instruction received from the device, it saves the address of the next instruction in the stack. So, this is the now it is the execution of the RST instruction. So, upon getting the RST instruction, the first thing is that it will be saving the return address into the stack. So, return address is saved into the stack and it the processor will jump to the appropriate appropriate entry in the interrupt vector table. And this IVT entry, so it has to redirect the processor to the actual service routine. So, as I said that each of this interrupt vector table the location like each so 8 such locations will constitute to one of these RST codes, and whatever be the value, based on that it will reach a particular location in the memory in the page 002 FF. In that page it will reach that particular location, and then it will start executing from that point. So, if your interrupt vector interrupt service routine is located from a different address, we should put a jump instruction there, so that now the system jumps to the processor jumps to that particular location. And so, that is the responsibility of the IVT entry, the interrupt vector table entry. So, normally it is we put a jump instruction there to go to the actual service routine, and the one thing that the service routine should do is that it should enable the interrupts using the EI instruction, because as soon as this interrupt occurs, when we go to the interrupt acknowledge cycle, this or the interrupt gets disabled, okay, the INTR gets disabled. So, it is important that the interrupt service routine it performs one enable interrupt to re-enable the interrupt process, otherwise the future interrupts will not be accepted. And at the end of the service routine, the rate instruction should be there, and this rate instruction will return the execution to the point where the program was interrupted. So, as we have seen that when in the INTA cycle, when the RST opcode is getting executed, so system saves the return address into the stack, and on getting the rate instruction, that address is retrieved and that address will be loaded into the program counter, so that the processor will return to the instruction which it has the instruction just after the one at which the interrupt was received. Okay. So, that way it continues. So, if we just look into the process more clearly, so I can say that if this is the program at which the interrupt has occurred, say when the instruction, so this particular instruction was getting executed, at that time interrupt has occurred. So, the processor will come to this, so one RST code will be generated from the device. If this is if this is the device, so somehow this device will produce an opcode for RST, opcode for RSTN instruction, and this will redirect the processor to some address. So, this will redirect, if this is the full memory. So, the first part is the IVT interrupt vector table, it will take the processor to a particular location in the IVT, and in that location I can have a jump instruction, jump 1000 say, so that my actual ISR is loaded from 1000. And while it has while this opcode RST is executed, the return address, that is this address, has been saved into the stack. So, this address is saved into the stack. Now, this from this from jump 1000, so it will come here. So, one important thing that it should do here is the enable interrupt, otherwise the interrupts will be disabled, and finally, there should be a rate instruction for return. So, when it gets the rate instruction, then from the stack this address will be retrieved from the stack, and the program counter will be loaded with this, so that my control comes back to this point. So, this is the sequence in which this interrupt will be executed. Now, so in case of 8085, so there are 8 such restart instructions, the RST instruction that I said. So, there are 8 such instructions named RST 0 through 7, and each of these would send the execution to a particular predetermined hardwired memory address. Okay. So, RST 0 is equivalent to call 0000. So, it will send the control to the location 0. Okay. So, it is same as pressing the reset button, activating the reset pin of the processor. or this RST 0. So, it will transfer the control to the location 0000. Then RST 1 is 0008. So, RST 2 is 0010, that is 16 in decimal. So, you see that what is happening is that in general, if the instruction is RST n, if the instruction is RST n, so this n is multiplied by 8, and whatever be the value, the processor will be jumping to that particular address. So, if it is a RST 4, then 4 into 8 is 32. So, it will jump to the address 0020 hex. Okay. So, that way at that location the interrupt service routine should exist. So, it may be a jump instruction to the actual routine, or if the routine is very small, as you see that between two successive RST locations. So, we have got 8 byte space. So, if my interrupt service routine is very small, then I can hold it in 8 bytes. So, that may be sufficient, or if it is not so, then we should put a jump instruction and go there. So, next we will have this the sequence is like this. So, restart sequence, it has got 3 machine cycles. In the first machine cycle, which is known as interrupt acknowledge cycle or INTA cycle. So, the microprocessor sends the INTA signal. So, INTA line is made low, and when the INTA is active, the processor will read the data lines, and it will expect that on the data bus there will be the opcode for a specific RST instruction. As I said, corresponding to the device. So, we have to map it onto one of these RSTs, and then that device should put that RST opcode onto the data bus. So, this is the first machine cycle or INTA interrupt acknowledge cycle. In the second and third machine cycles, what will happen is that the 16-bit address of the next instruction will be saved onto the stack, that is the PC high and PC low, those two values will be saved onto the stack, and then the processor will jump to the address to which to the of the specified RST instruction. So, this is the whole sequence of operation that is done in the restart sequence. So, this way the processor will be going to the interrupting to the interrupt service routine. Now, the location for the IVT, it may not hold the complete service routine, as I said. So, the routine may be written somewhere else, and we can have a jump instruction at the ISR location that may be kept in the IVT block. As we have already said that this interrupt vector table, it may have a jump instruction only for the actual service routine. Now, how to generate this RST opcode? So, that is a challenge. So, apparently it seems that how a device will generate the RSTN instruction code. Okay. So, this is very simple in the fact that the designers, they have made this RST coding in such a fashion, the opcode design of RST in such a fashion that it is quite easy to generate the RSTN opcode. So, we will see how is it doing it. So, as we know that opcode is nothing but one 8-bit pattern, that 8-bit pattern has to be generated on the response to the INTA signal. So, this is how we can we see that the RST opcode is generated. Okay. So, for example, suppose we are looking into the RST 5 instruction. So, in the RST instruction opcode, so if you look into the bits, then these bits are fixed, like say D7, D6, then the D7, D6, then actually this bit number 5, 4 and 3. So, the 3, 4 and 5. So, they will contain the actual number that the opcode, the n number that we have, the rest of the bits are all 1. So, this is so 3 bit number 3, 4 and 5. So, they will hold the pattern 1 0 1, and rest of the bits are all 1. So, you see that we can have a simple device, we can have a simple tri-state buffer like this, where for this particular instruction you see only the bit 4 has to be 0. So, bit 4 is made 0 and all other bits are tied high. Now, in the interrupt acknowledge cycle, this INTA bar line will be activated. As a result, this tri-state buffers will get enabled, and whatever be the content on this side of the buffer, they will be available here. And you see, as a result, all the bits excepting D4, they will get 1, only D4 will get a 0. So, that will be treated. So, this D7 to D0, so if it is connected to the data bus line of the processor, then it will be understood as the opcode for RST5. So, this so any other RST instruction, rest of the bits remain unaltered, only these bits, bit number 3, 4 and 5. So, they will be changing. Okay. So, RST0 to RST7, these bits will change from 000 to 111. So, that way we can very easily generate the opcode for the RST. So, this is the during interrupt acknowledge machine cycle, the first machine, so the microprocessor will first enable the activate the INTA signal. So, this will enable the tri-state buffers, and then the values that will come on the tri-state buffer which is the, so that will come onto the data bus. Okay. So, we will place the value onto the data bus and it will come there. So, for the RST5 code, so it is EF. So, that is fine. For any other opcode, that some other any other RST, some other opcode will come. So, that way this RST5 can be there, and the RST5 we know that it is equivalent to call 0028 a hex instruction. So, it will branch to the location 0028. Next, we answer the question, that is how long should the interrupt line remain high. So, this is a very pertinent question, because when you are designing a device to be operating with the microprocessor, and the device will operate will send interrupt to the processor. So, how long the device should be able to make that interrupt line high, so that it will be sensed by the processor. So, as we know, so the microprocessor will check the INTR line 1 clock cycle before the last T state of each instruction. So, one instruction will consist of a number of machine cycles. In the last machine cycle, last T state, last clock state, at that point it checks for the interrupt line. So, if this interrupt line becomes deactive before that, then that interrupt will not be sensed by the microprocessor. So, because this interrupt process is asynchronous, so it can occur at any point of time. So, it must remain high enough, so that this longest instruction can be executed. And in case of 8085, the longest instruction is the call instruction, that takes 18 clock cycles. So, if it takes 18 clock cycles and this INTA line is checked on the last clock cycle, so for 17.5 T states the line must be high. So, you can find out the frequency of the processor multiplied by 17.5, that will tell you the minimum duration that for which this interrupt line must be high, so that it will guarantee that if the interrupt occurs, the processor will definitely have a look into that. Okay. So, this way this answers the question that how long must the interrupt line remain high. And next question is how long should it remain high, how long can the interrupt remain high. So, can I keep it high continually. Okay. So, this question can be answered like this: the interrupt line must be deactivated before the EI instruction is executed. Now, as I said that any interrupt service routine, one of the important job that it does is to put the instruction EI, enable interrupt, somewhere. And as a standard practice, what is done is that this interrupt enable line is activated just before doing anything very much useful. Okay. So, before going into the actual routine, so this is done. So, any ISR code, so normally what we do is that if this is the beginning of the ISR, then first we push the registers that we have, whatever register this ISR will be using, all those registers are pushed, and after that we put the EI instruction. So, if somebody thinks that okay, I do not need the register values, then this part is absent. So, EI becomes the first instruction in the interrupt service routine, and when that EI is put, so if the EI is executed, all the interrupts get enabled again. So, you can understand now that if I do not deactivate the device, the interrupt pin coming from the device, interrupt signal coming from the device before this EI instruction is executed, then so it will be taken as a second interrupt. So, processor may take that interrupt line as the second interrupt. So, in the worst case, this is the situation that EI can be the first instruction of the ISR, and once the microprocessor starts to respond to the INTR interrupt, INTA becomes active. So, this becomes INTA becomes active, and then EI also gets active. So, another interrupt will be taken. So, it is a standard practice that interrupt should be turned off as soon as the INTA signal is received. So, whenever the device receives the INTA signal from the processor, it should turn off the interrupt line. So, that should be the practice to be followed. Now, coming to the other issues regarding INTR interrupt, can the microprocessor be interrupted again before completion of the ISR? So, that is once the interrupt has occurred. So, the processor is executing the ISR, can it be interrupted again before finishing the interrupt? Now, the answer is yes and no simultaneously, and it depends on the user, because you can see that you can once the interrupt has occurred, the INTR will be disabled and it will be enabled only after the EI instruction has been put. So, whenever the user feels that now I am ready to accept the next interrupt, should put the EI instruction. So, if the user thinks that no interrupt should be coming now once I am in the ISR, then EI should be at the end of the ISR. And if the user thinks that okay, after from the very beginning I am going to accept next interrupt, then that EI should be at the beginning of the ISR. So, this way, so as soon as the first interrupt arrives, all maskable interrupts are disabled. So, this is done by the processor and they are enabled by executing the EI instruction. So, now where do you put the EI instruction is the user's job. So, if the EI instruction is placed early in the ISR, other interrupt may occur before the ISR is done. So, that is the thing. Okay. So, at the point at which you are ready to receive the next interrupt, so you can put the EI there. Next, we answered the question that multiple interrupts and priorities, like how do I have priorities, like so I have so far whatever I have talked about. So, I have got a single interrupt line and a single device connected to the processor. Now, how can I ensure that a number of devices may be connected to the processor using the INTR line alone, and there will be priorities among the devices. For example, there may be say 8 devices connected with the microprocessor through the INTR line, and there will be priorities. So, the device 1 may have the highest priority, followed by device 2, device 3, like that. So, lower priority devices, so they will be allowed to interrupt the processor only if the higher priority devices they have not interrupted the processor. So, typical design is like this, that I have got all these interrupt lines coming from different processors, put them into this OR gate sort of thing, and then give it to the microprocessor's INTR pin. But if we do this, then the problem is that all these lines they are of equal priority. So, any of the interrupt coming, so it will be interrupting the processor. So, that we may not want. So, we may want that when this interrupt this device has interrupted, so none of the remaining ones should be allowed to interrupt. Similarly, the second one will be allowed to interrupt only if the first one has not generated any interrupt. So, this is how this can be done. So, that we will look now. So, the microprocessor can only respond to one signal on the INTR line. So, we must allow the signal from only one device to reach the microprocessor. So, there must be some priority assignment for that purpose. So, how to do this? So, for that purpose there is a special chip which is known as priority encoder, or chip number is 74366. This particular circuit, it has got 8 inputs and 3 outputs. Okay. The inputs are this is actually a priority encoder. So, a number of devices may be connected to this chip. So, the 8 devices can be connected to this chip, and the pin to which the device is connected will decide its priority. So, input 7 has the highest priority, input 0 has the lowest priority, and these 3 outputs they will carry the index of the highest priority active input. So, I think there is a diagram. So, in this diagram, so you see that 74138. So, this is the priority encoder that we have. So, this device, so this is actually going to this is the priority encoder. So, these interrupt lines are coming from there. So, it is this I0 to I7. So, these are the interrupt lines connected here. Now, this one this so there is a we can put this 3 output lines. So, 8 input 3 output, and these 3 output lines. So, they can be put through some tri-state buffer, and now you see that if say this encoder will ensure that if I7 has occurred. So, here you will get the pattern 1 1 1. If I6 has occurred and I7 has not occurred, then only you will get the pattern 1 1 0 here. So, that way whichever highest priority interrupt has occurred, so that value, that index will be available in these 3 bits. So, this 0 will be available here only if the none of the interrupts from device 1 to device 7 has occurred. So, only device 0 has interrupted. So, in that case you will get the pattern 0 0 0 here. So, this priority encoder, it has got an interrupt line. So, that is connected to the interrupt line of the processor, and in the interrupt acknowledge cycle. So, you see that this interrupt acknowledge cycle. So, this will enable this tri-state buffer. So, that these 3 bits will be available here, and they are so this for the RST instruction, you know that these other bits. So, they are all 1, this is bit excepting this bit number 3, 4 and 5, which can vary depending upon that RST n, that value of n. So, rest of the bits are all 1. So, that is done by this circuit tying all other bits to 1. So, in the when the interrupt acknowledge cycle is entered, and the processor enables this INTA bar line. So, this tri-state buffer gets activated, and all this n, the RST n, that n value will be available here. As a result, the processor will see one RST n instruction into this buffer, and it will go to the it will go to the corresponding interrupt service routine. Now, to send that interrupt acknowledge line to the individual devices. So, what is done? One decoder is employed here, 74138 decoder. So, here these 3 bits are connected, these 3 bits from this tri-state buffer. So, they are connected here, and whichever device has been allowed to interrupt the system, the highest priority device. So, that number is fed here. Accordingly, the corresponding output will be enabled, and that will go to the interrupt acknowledge for the device. For example, if say device 6 has interrupted. So, here you will get the pattern 110, and that 110 being fed here will enable this O6 line, and O6 line will send the INTA signal to the device 6. Others will not. Even if say 5, 6, 5, 4, 3, all of them have interrupted, only device 6 will get the interrupt acknowledge, not the others. Okay. So, this way we can handle these multiple interrupts and their priorities. So, opcodes from different RST instructions, they follow a pattern, be it D5, D4 and D3, they are having the opcode. So, that these bits will change, and then that will give the code for RST, and 111 is RST 7 and 000 is RST 0, other bits are always 1. So, this way we can use this this priority encoder for generating the RST code. Now, the problem that we have is that the only way to change the priority of the devices is to change the order of connecting the hardware. So, you cannot change that dynamically. So, like if you want to change the priority between device 6 and device 7, you want to make device 6 higher priority and device 7 lower priority, but in that case I have to connect device 6 to I7 and device 7 to I6. So, physically I have to change the order, but still for the small system. So, this is fine. So, it up to 8 devices. So, we can have this priority encoding. So, if you have got more number of devices, then possibly we can think about a multi-level priority encoder scheme, by which we can connect more than one 74366 chips and resolve interrupt priorities that way. So, this on the other hand, this maskable or vectored interrupt. So, there are 4 masked or vectored interrupts in 8085. They are known as 5.5, 6.5, 7.5. They have RST 5.5, 6.5, 7.5, and there is another trap instruction, which is the trap interrupt, which is now we will see later. So, all of them are maskable. So, first of all, this maskable interrupts are 3, 5.5, 6.5 and 7.5, they are maskable interrupt. The other interrupt that I have mentioned, trap, is a non-maskable interrupt and they are automatically vectored. So, RST 5.5, the vector address is 002C, 6.5 it is 0034 and 7.5 is 003C. So, when this interrupt occurs, then the processor will jump to the location 002C, then when 6.5 occurs it will go to 0034. So, you see that addresses, that the 002C is between RST 5 and RST 6, it is at the halfway between the two addresses for corresponding to RST 5 and 6, that is why it is called RST 5.5. Similarly, RST 6.5 is midway between RST 6 and RST 7, those two addresses. So, that is why it is 6.5 and 7.5 is after 7. So, 4 bytes away from 7. So, that way it is 7.5. So, that is why it is the halfway between the two. So, it has got the name like that.